everyone, so if you're in computer engineering, you've probably had worst case analysis drilled into your head, right? But what happens when that worst case almost never happens? Today, we're going to go beyond the textbook. We're going to explore how algorithms actually perform out in the wild, where average performance is often what really counts. So here's our game plan. We'll start by poking some holes in that worst case mindset. Then we'll dive into something called amortized analysis to get a much truer sense of cost. And from there, we'll use these ideas to figure out how to tackle some of the gnarliest problems in computing. All right, first up, let's challenge the way we've been taught to think. You know, in so many CS classes, it's all about an algorithm's worst case performance. And look, it makes sense. It's a safe, pessimistic guarantee. But let me ask you this. What if an operation is ridiculously expensive, but it only happens once in a blue moon? Does that one bad day really define the algorithm's entire personality? Probably not. It's time we looked at the bigger picture. And that leads us perfectly into this really cool technique called amortized analysis. The whole idea here is to figure out the average cost per operation, not just looking at one in isolation, but over a whole long sequence of them. So instead of getting all hung up on one single costly outlier, amortized analysis kind of smooths things out. It gives us a much more practical, realistic way to measure performance over the long haul. It's all about the average, not the exception. Now, to actually calculate this, we've got three main tools in our toolbox. Aggregate analysis is the simplest. You just add up the total cost for, say, 1,000 operations and divide by 1,000. Easy. The accounting method is a little more clever. It's like saving for a rainy day. You overcharge the cheap, easy operations and bank that extra cost as credit. Then, when a super expensive operation comes along, you use your saved up credit to pay for it. And finally, there's the potential method, which is kind of like physics. It thinks of the data structure as having stored energy that can be released to pay for future work. Okay, theory is great, but let's make this real. To see it in action, let's just look at a simple binary counter. You know, we just keep adding 1 to it over and over and over. Now, here's what's so interesting about this. Most of the time, what happens? Just the last bit flips from a 0 to a 1. Super cheap. But every now and then, like when you go from 3 to 4, that's 0011 to 0100, you get this cascade of flips. And if you only looked at that one operation, you'd think, whoa, that was expensive. But here's the magic. When you average it all out, the cost of those big, expensive cascades gets spread so thin across all the cheap operations that the average cost is constant. It's O of 1. This means that no matter how big the counter gets, the average time it takes to add 1 stays the same. That right there is the power of amortized analysis. It shows you the true practical cost. So what's the bottom line here? The crucial point is that this helps us understand how a data structure or an algorithm is actually going to behave in the real world under a constant stream of operations, which, let's be honest, is exactly what happens in any real system. Okay, let's switch gears a little bit. Now that we're thinking about performance differently, let's use that to classify problems based on just how hard they are. Because, believe me, not all problems are created equal. You can basically put all problems into two big buckets. On one side, you have tractable problems. These are the ones we can solve efficiently. Sure, they get slower as they get bigger, but it's manageable. Then you have the non-tractable problems. These are a different beast entirely. As their input size grows, the time to solve them just explodes exponentially. We're not talking about taking a few extra minutes. We're talking about taking longer than the age of the universe. And knowing which bucket your problem falls into, that is probably one of the most critical first steps for any engineer. It tells you whether you should even bother trying to find a perfect, exact solution, or if you need to completely change your strategy. So, what do you do when you run into one of these unsolvable, non-tractable problems? You can't just throw your hands up and quit. Nope, you get creative. This is where two really powerful approaches come into play. First, we can use randomness. We can design an algorithm that uses a bit of chance to quickly find an answer that is very likely to be the right one. The other tool is approximation. With these algorithms, you give up on finding the perfect answer, but in exchange, you get a good enough answer that's guaranteed to be within a certain distance of the optimal one. Okay, let's see how all of this stuff, non-tractable problems, the need for new strategies, all comes together in a classic real-world situation. So imagine you're running a factory. You've got these huge rolls of material, paper, steel, whatever. and your customers need smaller pieces of all different sizes. Your job is to figure out the best way to cut up those big rolls to fill all the orders while creating the least amount of waste. This is the cutting stock problem, and it's what we call NP-hard, which is really just a fancy way of saying it is a monster of a problem to solve perfectly. So to visualize it, just picture this simple setup. Your big roll is 100 units long, and you've got a list of pieces you need to cut out of it to meet your orders. Here's the core challenge. As you add more and more different piece sizes to your order list, the number of possible ways you could arrange them on a single roll just explodes. It's a combinatorial nightmare. Trying to check every single combination to find the absolute most perfect waste-free one, it's simply not going to happen. It's a non-tractable problem. And look, this isn't just about cutting paper. This is a perfect metaphor for tons of engineering challenges. Think about trying to pack data perfectly into memory blocks, or scheduling tasks on a CPU in a tiny embedded system with very tight constraints. In all of these cases, you can't afford to waste time searching for a perfect solution. You need a good enough solution, and you need it now. And that leaves us with a final thought, and it's a huge one for any engineer out there. Sometimes chasing that mathematically perfect, elegant solution is a fool's errand that will take forever. Meanwhile, a fast, approximate solution that's provably close to optimal is what actually gets the job done. And knowing when to make that trade-off, well, that's what separates good theory from truly great engineering.